Hello, I'm going to talk about a generalized matching reconfiguration problem, and this is joint work with Noam Solomon. The maximum matching problem is a fundamental combinatorial optimization problem, and we can consider either the unweighted version, where we would like to compute a maximum cardinality matching, or MCM, or the weighted version, where we would like to compute a maximum weight matching, or MWM. This problem has been extensively studied over the years in a variety of settings, but we are going to consider it from a perspective of reoptimization or reconfiguration. Let me try to explain what I mean by that. So we have now a graph, a network G, and some matching M for G. So let's assume that we are in the unweighted case. So M is some approximately optimal MCM for G, let's say 1.1 approximation. And you can imagine that M is being used for some practical purpose, such as scheduling. And in particular, the edges of this matching are giving service to some application. And now we are given access to a better matching M prime, a larger matching in this case. Maybe we are the ones who computed this matching in the background, or maybe we are given access to it by a third party. And the blue edges in this illustration are the edges of M. The black edges are the edges of M prime, the larger matching. And we are going to call M the source matching and M prime the target matching. And the premise is that we are now going to go from M to M prime. So the first question that you might ask is, why did we start from a small matching? There could be several reasons. One of them is that maybe we have limited resources. Maybe the matching is not computed by us. Maybe we receive it from a third party. And another reason might be that the matching M might have been really great, maybe even the maximum matching for the graph, but it was a while back, and the network G has changed in the meanwhile, either by temporary failures, like communication links that crash, or by permanent changes that are part of the normal behavior of the network. One way or the other, the matching that we have for the current graph is not good enough, and we would like to switch to a better matching. Okay, so we are going to use here a gradual transformation process. So we are only gradually going to move from M to M prime. We are allowed to make just a single edge change per step to the output matching, starting at M and eventually coinciding with M prime. And we also require that the intermediate configurations along this process will be matchings, and also large ones, but we'll get to this in a second. Okay, so why should we employ a gradual transformation process? Why can't we transform from M to M prime instantaneously? So here, first of all, this network could be very big, and it might be prohibitively expensive to carry out such a transformation instantaneously. In fact, it could be even infeasible to do this at once. And here you can imagine that the edges of M that are giving service to some application are hardwired in some physical sense. Okay, so we are going to apply a gradual transformation process that could be slow. Okay, so what we would like to do is just abandon all the blue edges and move instantaneously to the black edges and then designate them as the blue edges, so to speak, so that now they are the ones to give the service. But this is not what's going to happen, right? So, and this also explains why do we need to have large matchings throughout this process? Because we would like to continue the service throughout this possibly very slow transformation. And we are continuing this service with the edges of the output matching that gradually changes. So if the output matching is always guaranteed to be large with respect to the sizes of the source and the target matchings, then the service that this matching will provide will be reasonably good. And you see that the size lower bound that we will try to enforce is smaller by 1 unit than the sizes of either M or M prime. We could assume that the size of M prime is no smaller than the size of M, but one can also imagine situations where we are going to switch to a worse, to a smaller matching due to some practical considerations. Okay, so we are allowing this unit of decay, unit of slack. And okay, so now why should we allow this unit of slack? Consider these two black edges. We would like to move them to the output matching, but we cannot do this because they are incident on this blue edge that is currently in the output matching. So in order to add one of these black edges, we first need to delete this blue edge. So we are starting off by this unit of loss to the size of the matching. And in fact, any black edge that you would like to add to the output matching in this example will trigger this loss. Okay, so we have to have this unit of loss. And you know, once we have deleted this blue edge, we can designate this black edge as an output matching edge. And later we can designate this one. Okay, so by coloring the edges blue, I mean that these edges go to the output matching. And you know, let's say that I would like to put this edge in the output matching. To this end, I first need to delete the blue edge incident on it. And so this is what we are going to do. We are going to employ this gradual transformation process until all the edges of M prime become the output matching edges. But you see that even this 1 unit of loss is not always sufficient. Okay, so let's say that the two blue edges are the edges of the source matching, and we would like to move to the two black edges. But adding even one of the black edges requires us first to delete the two blue edges from the output matching. Okay, so this incurs 2 units of loss. Okay, so sometimes we need 2 units of loss to the size of the output matching, but we never need more than 2 units of loss. Okay, so in the previous work by Ito et al., they studied the complexity of several reconfiguration problems, including the matching reconfiguration problem, and they gave a polynomial time algorithm for this decision problem of whether or not there exists a gradual transformation, as we discussed, where you never decrease the size of the output matching by more than 1 unit. Again, it's not always possible. So the answer should be either yes or no, if it's possible or not. And their argument, I would say, is non-trivial, and it is in particular based on the Edmonds-Galai decomposition. And they also conjectured that one can get a similar result for weighted matchings. In the same paper, they studied some other problems. So for the minimum spanning tree problem, and more generally for metroid problems, they gave a polynomial time algorithm. And they also showed that quite naturally, the reconfiguration versions of various NP-complete problems is p-space complete. And they considered problems like maximum independence set, minimum vertex cover, and more. But it's not always the case that the reconfiguration version of any NP-complete problem is p-space complete. And it's interesting. It's an interesting direction to explore this question more deeply, because currently it's not fully understood. Now, there is a large body of work on graph reconfiguration problems, and the setup is rather general. So you can imagine that we consider a configuration graph for some search problem, such as maximum matching. And the vertices or the configurations correspond to feasible solutions of this search problem. And the edges correspond to adjacency relation on the set of configurations. And so there are some details that I don't want to get into, such as that this adjacency relation ought to be polynomial time testable. But there are quite a few questions that we can ask. So the first one could be, is there a path between two given configurations, which is the analog of whether or not there is a gradual transformation process between these configurations. We can also restrict this path to being of a certain length. And we can also pose other restrictions on the vertices that belong to this path. We can also ask more global questions, such as, is this configuration graph connected? Maybe the diameter is bounded by some threshold, and so on. And a part, or maybe even a big part of this line of work, is motivated by practical applications, such as to motion planning. So here, for example, you can consider a set of robots that would like to move along edges of a graph, and obstacles could be located at some vertices in the graph, so on. Reconfiguration problems could also model evolution, and this has been done in ontology evolution, biology evolution, and it's very intimately related to questions in computational genomics and gene editing in particular. There are applications to Markov chains, and in other, I would say, practical applications, broadly speaking. But also from a more theoretic perspective, most of the combinatorial games and puzzles that you can think of can be cast naturally as reconfiguration problems. Now, if you think of a configuration as a set of elements, which is something that you can almost always do, then typically a pair of configurations is defined to be adjacent if their symmetric difference is precisely 1. And of course, this is very restrictive. It's not always the case, but I would say that in essentially every work that I'm familiar with, the idea is to pose restrictions on the adjacency relation so that we'll get a decision problem, whether or not, for example, there is a path between two given configurations, and so on. Now, what we are proposing is quite different. We would like to relax the problem by introducing an additional parameter, delta, that controls the symmetric difference size between adjacent configurations. And we notice that when delta is equal to 3, there is a simple linear time gradual transformation process. And specifically, take any graph G, any source and target matchings, there's always a gradual transformation process for M to M prime, where you're allowed to make at most three edge changes to the output matching, where the matching size never goes below this threshold. So we still have this -1, this is inevitable. The running time of this transformation is linear in the sizes of the matchings. And if you think about it, this is optimal with respect to all the parameters. You cannot reduce delta from 3 to 2 unless you are willing to incur 2 units of loss. You can think of the 4 cycle, and you cannot hope to reduce this -1 to shape this -1. And here too, you can think of the 4 cycle. And of course, you can increase delta, but then I can use as a counterexample a longer cycle. Now, this is a simple theorem to prove. It is more challenging to generalize it for weighted matchings. So here, we don't want to go down below the weights of the source and target matchings by more than W units, where W is the maximum edge weight. And we can massage this parameter to get something that is closer to the average weight, or at least not maximum edge weight in the entire graph. And the running time is as before, it's linear in the sizes of the matchings. And more interestingly, perhaps, if we are increasing the symmetric difference size delta to 1/epsilon, then we can make sure that the weight of the output matching never goes down by more than a factor of 1 - epsilon. And this is, I believe, more interesting. And so in general, we can get the maximum of the two, whatever is better. And here too, in general, what we get here is optimal with respect to all the parameters. Now we'll see an application of this gradual transformation theorems to the area of dynamic matching algorithms. So first, a quick recap on dynamic matching algorithms. Let's assume for simplicity that we have n fixed vertices, but the edges come and go. Now, at every update step, a single edge is either inserted or deleted. And let's assume that we start from an empty edge set. Now, following every update step, the algorithm has to update the matching of interest. And for concreteness, let's assume that this is a maximal matching, and therefore also a 2 approximate MCM. Okay, and we'll see a very naive algorithm for maintaining a maximal matching very briefly. So the first edge comes, and the algorithm adds it to the matching. There's no other option. The blue edges are the matched ones. Then the second edge comes, and the algorithm doesn't have to do anything. This is already a maximal matching. The third edge comes, the algorithm adds it to the matching, and so on and so forth. And it's not like we have only insertions. Here's an example for a deletion of the matched edge. And then the algorithm can cope with this deletion by adding this edge to the matching in its place. And the most basic goal of an algorithm in this context is to achieve a small update time. Okay, so the update time of an algorithm is the time it takes the algorithm to update the matching following a single update step, and we can either try to optimize the amortized bound or the worst case bound. And there are a bunch of dynamic matching algorithms with very small update time bounds, even in the worst case. Okay, so it's not like this area is fully resolved. There are many open questions, but I just want to mention that there are a lot of non-trivial algorithms with very low update time bounds, also in the worst case. Whereas for the recourse bound, which is another interesting and important quality measure, very little is known. And so the recourse bound measures the number of changes to the output matching per update step. And in the naive algorithm that we saw, we made just one change to the output matching, but it doesn't have to be this way. Maybe following a single update step, we change the matching completely, yet the update time could still be very low because maybe we are just changing pointers from one matching to another. It could be a constant time operation, but the recourse bound could be huge. And so, although the update time of an algorithm is low, sometimes we would like, and this is important, sometimes we also need the recourse bound to be low because maybe this matching algorithm is embedded inside a bigger data structure or algorithm, and a high recourse bound will trigger significant blowups to the bigger data structure or algorithm. And controlling the recourse bound is also important for other reasons, and you can take a look at the paper for more reasons. So we would like to control the recourse bound, and perhaps surprisingly, almost all known dynamic matching algorithms that have a low update time incur a high and very high worst case recourse bound. And sometimes this algorithm incur a high amortized recourse bound. Okay, so to remedy this, we propose the following theorem, which can be viewed as a black box reduction. And I'm starting with the unweighted case. So let's fix an arbitrary beta, parameter beta, at least one, epsilon greater than 0, and let t be some runtime function. And n is the number of vertices in the graph. So what this theorem says is that if we have as input any dynamic algorithm A for maintaining a beta approximate MCM within update time t, subject to some condition that I'll explain shortly, then we can use this algorithm as a black box and transform it into a different algorithm, A prime, which maintains a beta times 1 plus epsilon approximate MCM, a very different matching possibly, but with a similar approximation guarantee, and within a similar update time of t plus some constant over epsilon. And this new algorithm also has a worst case recurse bound of some constant over epsilon. Okay, so the transformed algorithm A prime enjoys the same guarantees on the approximation factor and update time as A, almost the same, not exactly the same, but it also achieves a worst case recurse bound of roughly 1 over epsilon. And the condition that I omitted is that this black box algorithm A needs to be able to output efficiently the edges in the matching that it maintains, within time linear in its size. Now, this condition may seem very restrictive, but in fact, I'm not aware of any dynamic matching algorithm that doesn't meet this condition, that doesn't satisfy this condition. So I'm not sure how restrictive this condition is, but I should mention that if we don't have this condition, so that we don't have this linear time guarantee, then we'll have a blow up in the update time of the transformed algorithm, which is this blow up will be proportional to the slack that we have here in the time needed to output the matching. Okay. Now, if the original update time bound T is amortized, or worst case, so is the resulting time bound, T plus roughly 1 over epsilon. And in any case, the recurse bound always holds in the worst case. Now, we talked about the setting where edges come and go and the vertices are fixed, but even if we consider a generalized setting where we have both edge and vertex updates, or just vertex updates, it will still hold this transformation. And this is an optimal bound on the recurse bound when we are talking about an approximation factor of roughly 1 plus epsilon. So we show that if we would like to maintain an approximate, a 1 plus epsilon approximate MCM, you cannot get asymptotically better than 1 over epsilon recurse bound, even for incremental or decremental settings, and even in the amortized sense. And I should mention that if 1 over epsilon is constant, then obviously it's optimal. So here I implicitly assumed that 1 over epsilon is some super constant parameter that depends on the graph size, on n. So we cannot do better than 1 over epsilon. 1 over epsilon is the right answer for the problem. And finally, we generalize this transformation to weighted matchings. Okay, so now let's use another arbitrary parameter W, and let's assume that the edge weights are always contained in this range between 1 and W, not necessarily integers, but they are in this range. And we can get similar transformation. We get the same bound on the approximation guarantee, but the update time will increase not by an additive term of 1 over epsilon or constant over epsilon, but rather W times this constant over epsilon. And the worst case recurse bound will grow from constant over epsilon to constant times W over epsilon. Okay, so you see this W everywhere. We just replace 1 by W. And so this is what we get. Now, I'm not going to give any technical details behind the proofs of these theorems. I chose to focus on the statements themselves and also on the descriptions of the settings, particularly the dynamic setting. But I want to conclude with the following. First, we saw that by relaxing the parameter delta, which controls the symmetric difference size between consecutive or adjacent configurations, is very useful. It's useful for the matching reconfiguration problem, but maybe it's also useful for other reconfiguration problems. Now, the main takeaway message of this work is the applicability of the matching reconfiguration problem to dynamic matching algorithms. And I believe this applicability deserves further study, and I'm not necessarily talking about improving the dependence on W in the theorem from the previous slide, the one on the black box reduction for maximum weight matching, which is also a nice question. I'm talking more broadly than that. And also, maybe there is a similar applicability for other reconfiguration problems. And maybe in this way, we could get improvements for other dynamic graph algorithms outside the scope of graph matchings. Finally, graph reconfiguration captures an inherent tension between two somewhat contradictory objectives. The first is a global objective of transforming one global solution to another, and the second is a local objective of carrying out this transformation gradually so that consecutive configurations along the way or adjacent configurations should be very close one to another. Okay, so we have this parameter delta that controls how close they are. It would be very interesting, I believe, to study connections to other settings that capture a similar tension beyond dynamic graph algorithms. So one example could be to distributed computing, another could be to property testing, also streaming algorithms, and more. And I'll stop here. Thank you.